Hello gang, in this video we're going to go over molecular equations, complete ionic equations, net ionic equations, and spectator ions. We're going to go through some specific examples and know how to convert between the three equations and how to identify what these spectator ions here. So let's jump into it, and I got some examples here. So this is one example here. Chlorine dioxide, ClO2, is used in water treatment as a powerful oxidant and bacterial disinfectant. A common reaction used to produce chlorine dioxide is shown below. And here's our equation here. It's like an equation, except with an equal sign we have a arrow, and we have these are the reactants, and going to the products here. Here's our chlorine dioxide that we're producing here. Now, this is one type of an equation, and the above reaction is called a molecular equation. Molecular. And it's called a molecular equation because it's written in terms of the molecules. So this reactant is a molecule, this is a molecule. All of these molecules are neutral. They have no charge. And even if they're ionic and they may produce ions when they're dissolved in solution, we're written in this molecular form as a neutral molecule. It's called the molecular equation here. Now, we'll continue here. So, however, the ionic compounds are dissolved in, when the ionic compounds are dissolved in water, they split into cations and anions. So that's positive charges and negative charges. And please write the cation and anion for each ionic compound, including the acid, in the reaction. So if we look here, this is sodium and ClO2, that's chlorite. This splits up. This is an ionic compound because it's attached to sodium, the metal. Any metal in group 1 or group 2 will essentially dissolves with varying solubility, but this will dissolve into anions, and sodium becomes Na+. So maybe I'll write the whole molecule here. So NaClO2 and dissolved in water, which is aqueous, becomes Na+ and ClO2-, chlorite. All right, so that's this one here. This is the cation, this is the anion, because it's negatively charged for the anion and positively charged for the cation. Now this one here, we have another sodium. So this one breaks up to sodium, this is hypochlorite. And when it's dissolved in water, it breaks up into Na+, and there's no 2 there, just OCl, and that's an aqueous, and OCl negative here. Technically, we should put aqueous here to show that they're dissolved in water. Okay, now let's look at this next one. Here's our acid, hydrochloric acid, HCl, and acids dissociate in water. That means they break up. So the HCl becomes H+ and Cl-. Now, H+ doesn't really exist in water. It actually complexes with the water molecule H2O to make H3O+, but we're just going to keep this simple right now and say H+. Some people hate seeing H+ like this, but just so you know, this actually reacts with water. So that's splitting up the reactants here. Now we got to look at the products here. Now this is ClO2, and it's neutral. It's chlorine dioxide, so it's a neutral molecule. It's not an anion like ClO2 negative. ClO2 negative is an anion. So because this is a molecule, it's considered a molecular compound or a covalent compound. It's not an ionic compound like these ones here or an acid here. So this one does not break up when it's dissolved. It remains as ClO2. So this stays as it is. And here we have another sodium and chlorine, so those break up. So Na and Cl, aqueous, breaks up when it's dissolved in water, dissociates into Na+ and Cl-, AQ. And here we have water. Water is dissolved in water. That doesn't really make too much sense. So I'm just going to erase this AQ here and make it L. Usually you see it as just liquid because it is the solvent in here. And this isn't an acid. Water can act as an acid, but in this case, it's just water. It's not broken up. It's just like a covalent compound. So just like this chlorine dioxide, it doesn't break up either. It just stays as H2O. So we just have these 1, 2, 3, 4 compounds that break up when they're dissolved in water. Okay, so now that we've identified what molecules dissociate and what molecules don't dissociate, we can write something called the complete ionic equation. Here's the molecular equation in molecular form. The complete ionic equation is this exact same equation, except we've written the ionic, we'll write the ionic compounds in terms of their ions, in terms of the cations and the anions. Here's a cation for this one, and this is the anion for this one here. So let's write that out. So first we're going to start off with this NaClO2. Now it's dissolved into the cation and anion, and these coefficients here, these stoichiometric coefficients, they matter because they're here to help balance the atoms with the products and the reactants and show the ratios between them. So we need this 2 here. So rather than just being Na+, we have a 2 here, so it's 2 Na+, 2 Na+, aqueous, and the ClO2 minus, aqueous. So now we've broken up this one. Now we'll look at the other ionic compound, which becomes NaOCl minus, sodium and hypochlorite. So we'll just write that in its ions, Na plus and OCl minus. We'll say it's aqueous because it's dissolved in water. There's one more of the acid, right? The hydrochloric acid, so there's 2 H pluses and there's 2 Cl minuses. 2 H plus and 2 Cl minus there. And these are also dissolved in water, so they're aqueous. So that's the ionic form of, this is the ionic form of the reactants. This is one compound plus 3 Cl minus, and we have a water H2O liquid. I'll make these aqueous and aqueous there. Okay, so this is one compound here too. That's just been broken up, dissociated into its ions. And this, in all its glory, this is our complete ionic equation. So it's the same equation as here, but rather than writing it in molecules, in the molecular form as molecules, we write the ions as they are. So we dissociate, we break up the ionic compounds into their respective ions. So this is our complete ionic equation. Now there's something called the net ionic equation. And if we notice that we have some of the same ions on both sides of the reactants and the products. So we have sodium on this side, and we have chloride on this side, and same thing on the product side. We also have a sodium and chloride here too. So we can cancel these out. So this sodium is not involved in the reaction, and this chloride here is not involved in the reaction either. So that's because we have them on the reactant side and on the product side here, the product side and the reactant side. They don't change form, they don't help create new molecules per se. They're just there hanging out in the solution, not part of the reaction. So because of that, they are called spectator ions. Spectator ions. And they're called that because in a way you can think of them as observing the reaction but not participating in it. Okay, so we'll circle them. Let's circle them here. So there's sodium, chloride. There we go. So we circled them, that's done. Now, let's say we only care about the species, like the ions and the molecules that are actually react. We only care with the stuff that's reacting. We don't care about the spectator ions. So we're going to write this equation without the spectator ions here. And I'm going to do it right below. Just going to give a little bit of room here. Okay. So these two sodiums here and this sodium here, this is 3 sodiums on this side, 3 sodium ions, and we have on the reactant side and we have 3 sodium ions on the product side. So these 3 sodium ions are going to cancel out with these 3 sodium ions here. So those we're not going to include in ClO2 minus. And what else do we have? We have an OCl minus plus OCl minus aqueous. And we have, because we don't have an OCl minus on this side, so it's involved in the reaction, so we'll include that. It doesn't cancel out on both sides. We have these H pluses on the reactant side. We don't have H pluses on this side, so and we have 2 H pluses. Now we have chlorine or chloride on this side of the equation, the reactant side, and we have chloride on the product side. But we have, to make this balanced, this whole thing balanced, we have 2 chlorides here and 3 chlorides here. So 2 of these chlorides cancel out with 2 of these 3 chlorides on the product side. We have 2 chlorides on the reactants, 3 chlorides on the products. So these are going to cancel out, but we're still going to have a chloride on the product side. Well, maybe we'll get to that in a minute. I won't write chloride here because I'll write it in order. So these 2 chlorides have canceled out, so we won't include them on the reactants. Now, as we go to the products, we have ClO2 here. We don't have a ClO2 on the reactant side, so this is ClO2 aqueous, AQ. These sodiums are, I should have circled this here because it's a spectator ion. 3 sodiums here cancel out with these 3 sodiums here. So that's gone. Now we lose 2 of these 3 chlorides to here. So 2 of these chlorides cancel out with 2 of these chlorides. So we have 1 chloride left on the product side. And we have water. Now, water is a solvent, so we do have water everywhere, but we don't have water reacting as a reactant. We're producing water, and it doesn't cancel out on both sides. So we'll include the water, plus H2O liquid. Okay. So this is the net ionic equation. It's the equation, ionic equation in ionic form, not molecular form. We show the ions without the spectator ions involved. All right, so after all this, we've represented a chemical equation using 3 different equations, the molecular equation, the complete ionic, and the net ionic equations. Please state 1 pro and 1 con for each of these 3 equations. Which one is your favorite? So I'm going to scroll up and start at the top and work my way down. So the molecular equation right here, the pro of this, of seeing it this way, is that these are the actual molecules that we add or that we create, the salts that we can create or produce from it. So we don't add an ion in a solution. Like when we're mixing reactants together, you got to add molecules. You don't have a bucket of just chlorite by itself with no counterion. Chlorite always comes from some cation here. So this shows the actual molecules that we have in the reaction. But the pro or the con is that not all of these react in this way, and they don't react in this form. And not all of the atoms here are involved in the reaction, so it doesn't help in that regard. The complete ionic, now this is I crossed a few things out, but this complete ionic, it shows the molecules and ions as they are in solution. So this sodium chlorite doesn't exist as sodium chlorite when it's dissolved in water. It exists as sodium ion and the chlorite ion, anion. So this is what's showing, this shows the species that are actually present in the solution as they are. A con is that we have the same species, say the same ions on the reactant side and the product sides for the spectators. So it shows the spectators, and it doesn't, and these spectators don't participate in the reaction, although they're included here in the chemical equation. So it could be confusing to see why we have the same species on either side and they're not participating. The net ionic is nice because it only shows what's reacting. So we can ignore all the other species that are not that do not participate in the reaction. They're not part of the reaction. When we do stoichiometry or chemistry, we may just focus on this equation because that's what's actually the chemistry that's actually happening, or when we're dealing with redox reactions. However, the con is that we don't have the complete picture of what's in the solution. We don't know, is there sodium here? Is there calcium, magnesium? We don't know all the species present. It hides the species, the ones that are not participating in the reaction. So there's pros and cons for each one of the reactions. And my favorite, it really depends on what we're doing, but I generally like this net ionic one here because this one hones in on what species are actually reacting, and we're not getting cluttered up with these spectator ions or have to kind of break things up to work with the equation. Although all of them are great, but I generally use this one more when doing chemistry. Good. Okay, so there's the pros and cons and my favorite. Here's one more example, and you're welcome to pause the video and see if you can work through this. And I'm just going to work through it now otherwise. So here we have another similar equation here. And let's see if we can balance the equation. You always want to check to see if it's balanced, but this is already, oh no, this is not balanced. So we have 1 chlorine, 3 chlorines on this side, and we have 2 chlorines on this side. So we need another chlorine. If we add another chlorine, say here, say we put a 2 there. That's supposed to be a 2. Put a space here. If we put a 2 there, now we have 2 sodiums. So we have too many sodiums on this side. So we need to put a 2 here to make sodium. But now we have too many of these ClO2. Now, in terms of just balancing the atoms, we can put a 2 there. So this balances the ClO2 with 2 ClO2s here. We have 2 sodiums, and then 1, 2, 3, 4 chlorines total. 2 chlorines here, 2 chlorines here. Okay, we're balanced. Good. All right, that's done. State the type of equation given. Well, we're seeing them in their molecular form. They're not in their ionic form. So we're seeing ionic compounds with the cation and the anion together. So this is the molecular equation, EQN equation. Write the complete ionic equation. So that's with all the ions, the complete. We're not removing any ions. So here's an ionic compound that will split up. So it's 2 Na+, and there's 2 ClO2s, negative. Now, this has to be negative because the sodium is positively charged. It splits up into cation and anion. And chlorine in water, it doesn't break up. It's a molecular compound. Let's put AQ here, AQ here, AQ here. This is chlorine gas dissolved in water. You may see this as a G here. In the product side here, we have 2 ClO2, so 2 chlorine dioxide. Now, it's not an anion. It's not an anion, and it's a covalent compound, so it doesn't split up. So 2 ClO2 aqueous plus. Now this splits up sodium chloride. So we have 2 Na plus and 2 Cl minuses. There's the complete ionic equation. Let's circle the spectator ions. So we have 2 sodiums here and 2 sodiums here. We have, oh, that's it. Remember this is an anion and this is not an anion, so they don't cancel out. Okay, so that's done. Let's see, we stated the type, we wrote the complete ionic equation, we circled the spectator ions. Let's write the net ionic equation, so that's without the spectator ions. It will be, so sodium's gone, and there's 2 sodiums here, cancel out with 2 sodiums here. So we have 2 ClO negative 2 AQ plus Cl2 aqueous, and our chlorine dioxide aqueous, and our 2 chlorides, which don't cancel out. Oh, this should be AQ, and I'll put an AQ here. Good. All right, that's it. If you were here, I would high five you. But there's those example. Another example. Here's 2 examples here. and see if we can write the complete ionic and net ionic for each of the reactions. Well, here's potassium. It's in group 1. In terms of naming, we sometimes call this a type 1 metal, so it breaks up into anions. First, we should see if it's balanced. You never want to assume it's balanced. There's 2 potassiums, 1 sulfate, 1 barium, 2 nitrates. Oh, but there's a 2 here. Okay, we're good. So we'll split this up. So this would be 2K plus aqueous plus the sulfate, and there's just 1 sulfate. And there's 1 barium, so Ba2 plus aqueous. There's 2 nitrates, and that goes to potassium nitrate, so potassium breaks up, and it's aqueous, and the nitrate breaks away, dissociates, aqueous, and then barium sulfate. So this would break up, right? Because it's barium and sulfate, and it can dissolve into its respective ions, the barium 2 plus and sulfate 2 minus. But it's not dissolved in the solution. If it was dissolved, it would break apart, it would dissociate. But it's not broken apart because it's in the solid form, solid phase. So as a solid, it's not going to break apart into its respective ions. It can't do that. It's going to stay as it is, as a molecule. So BaSO4 solid. Okay, so that's the complete ionic equation here. So maybe do a star. Now our spectator ions, oh, I'm supposed to have a 2 here, 2 potassium C, and then a 2 nitrates. There's a 2 here, so 2 potassiums, 2 nitrates. So these 2 potassiums cancel out, the 2 nitrates cancel out, and the barium and the sulfate, they can't cancel out because they don't have any of their ions on this side. There's no barium ion and there's no sulfate ion, just the barium sulfate. It's molecular. It's not an anion, so it doesn't count in terms of canceling out. So the net ionic equation is without those spectators, so SO4 2 minus aqueous plus barium 2 plus aqueous goes to barium sulfate. Solid. So there's our net ionic equation. Complete ionic, net ionic. Just what participates in the reaction. Okay, so the complete ionic is, we'll break this up. Sodium carbonate breaks up into, oh, first we should check if it's balanced. 2 sodiums, that's good. 1 carbonate here. Oh, look at this. This is CO2. And this is CO3. So this doesn't balance. We have 1, oh no, we balance because we have an oxygen here. Yeah, usually if you see coefficients, it is balanced, but I always like to double check. This is CO2, but we have an oxygen. There's 2 chlorines, 2 hydrogens, okay, we're good. All right, we're balanced. Good. Okay, so we'll break it up. So we have 2 sodiums. So 2 Na pluses. And we have 1 carbonate, 2 minus, aqueous, and hydrochloric acid breaks up into H plus. Now technically the H plus complexes with water to make H3O plus, but we'll keep it simple. And Cl minus, there's 2 of them. Sodium chloride, of course, breaks up. And chloride, AQ. And this is a gas, and it's a covalent compound, so it doesn't break up or dissociate. It stays as it is. And same with the water. It doesn't break up. It stays as it is. Okay, so the spectator ions are, we have 2 sodiums and 2 sodiums. We have a, do you see this 2 here? I got to put this 2 on this chloride. Both of these have a 2 attached to them. And these 2 chlorides cancel out on either side of the equation. So the net ionic equation is, without the spectators, CO3 2 minus AQ plus 2H plus goes to CO2 gas and H2O liquid. All right, gang, that's it. Hope you enjoyed it. Thanks again. Cheers.